In this video, we present a method for learning to correct errors in inverse depth images of 3D reconstruction. Our approach uses two dense reconstructions of the same scene that differ in quality. Here, we show a mesh generated from laser data on the left, and one generated from stereo camera data on the right. While the camera reconstruction contains more information in some areas, especially around tall objects such as buildings, it is of lower quality. For example, notice the holes in the road or the smearing between the cars. To obtain 3D meshes from laser and stereo camera data, we use the Borg dense reconstruction system. In addition, the stereo camera is used for localization through visual geometry. An OpenGL renderer produces features from both reconstructions, and the difference between the inverse depths from the camera mesh and the laser mesh is computed. Convolutional neural network is then trained on the camera-only mesh features to predict this difference. Here we illustrate features produced from the two meshes. From the higher quality laser-only mesh, we generate inverse depth images. From the lower quality camera-only mesh, we generate images that contain inverse depth, the area of the mesh triangles, the surface normals, the aspect ratio of the triangles, and the angle between the surface and the camera. We use two inverse depth images to compute the signed error labels when training the neural network. This allows us to predict not just where errors happen, but also their magnitude and direction. We generate 2D features along the original trajectory in 3 Kitty sequences, and we use these features plus the original RGB Kitty images to train and evaluate a CNN. The network learns to regress to pixel-wise error and inverse depth with respect to the higher quality mesh. Because we regress to the error in inverse depth, we can use the predictions of the network to directly apply corrections to the inverse depth images of camera-only reconstructions, as illustrated here. The network successfully identifies errors such as holes in a mesh or incorrectly shaped cars. To get an idea of what features are most relevant for determining reconstruction errors, we run an ablation study. We hold back each feature in turn and fine-tune the network to see how much it can recover with that feature missing. Unsurprisingly, inverse depth is very important in completing this task, and the network cannot recover if it is missing. We also see in this figure that surface normals and RGB images are also particularly important for the task of predicting reconstruction errors. For more information, please visit our booth during the poster session.